Hi, so we'll start talking about shell sort. First, we talk about the idea behind it. So we've just studied insertion sort, and we said insertion sort is in square quadratic, not very fast. Now, um, you might have recognized this is that with insertion sort, the biggest problem is when the number of elements gets really large, then it takes a really long time to insert an element at the right place, right? So imagine in the extreme example, a very small item at the end of the list. The rightful place is at the beginning of the list, so it has to travel the full length of the list. But it only travels one index at a time. So it's one step at a time, right? That's why it's so slow. And so I can actually show you a kind of a nice animation from our favorite visualization tool. Like this is doing an insertion sort and it's almost done, but there are some small elements at the end here. And you can kind of see when I play this, it just takes a long time to travel to the beginning of the list. So that's the problem. Now, what if instead of moving the element just a single position at a time, we can move them over a longer distance or over a bigger gap closer to the destination every time. So that's kind of the basic idea of shell sort. So just a bit of history. So shell sort is named shell sort because it's named after its inventor, Donald Shell. It was invented in 1959. And the best way to explain shell sort, how it works, is actually to look at a demonstration. So here is a list. And we said that instead of moving item one position at a time, we want to move it over a longer distance. Now, what is this longer distance? Well, what is the longest distance in this list? Well, there are 8 elements, so the longest distance or the biggest gap would be 7, right? But there's only 2 elements that are 7 index apart from each other, 6 and 8. So really, that isn't very useful. We're not moving very many things. On the other extreme, the smallest distance would be just 1, but that would kind of brings us back to the insertion sort, which is something that we're trying to improve upon. So between 1 and 7, how about let's pick something in the middle? We'll start at 4. All right, so let's see how that goes. So the numbers 6 and 0, they are 4 positions apart. So we'll say 6 would be the sorted part in the insertion sort, and then 0 would be the unsorted part. So we just take 0 and compare it to 6, and we have to swap it because 0 is smaller than 6. So we swap it, and then we move on. We move on to the next element. Okay, now we're trying to sort 3, but the gap from 3 is kind of 4 away, so we're trying to compare 3 with 10. And again, we have to swap them, so let's do that. And there it goes. 3 is in the right place now, so we keep moving. The next unsorted index would be 9 and 2, and for these two we don't have to swap them, so we move on. And then finally when we get to 8 and 5, well, we're done. And as you can kind of see, many of these numbers, they are already fairly close to where they should be in the sorted list, so that's good. And even though this list is not completely sorted, it's partially sorted. This is called 4 sorted because the gap was 4. Okay. However, as we said, we're not done. So what do we have to do? We need to kind of decrease the gap, and then do the same operation again, right? Now, what can we decrease the gap to? Well, we know we ultimately has to get to gap of 1. However, even though it might be okay in this very small list, in a very big list, say a list with I don't know, 1 million elements, and then if if half of the well, if it's 500,000 sorted, then we go immediately to 1, then we're still running an insertion sort on 500,000 items, which will take a long time. So we don't want to decrease the gap so drastically, right? So what's the next best thing we can do? Well, we can just have it like we pick the initial gap to be half of the entire length of the list. So let's just have it. So in this case, we're going from a gap of 4 to a gap of 2. And as a matter of fact, I would ask you to pause the video and try to sort this list so that it's 2 sorted when you're done. Assuming you've tried it yourself, let's go through it together. So we start at gap is 2. We start at position 2, right? 2. Look back at 2 positions back. We compare with 0. It's good. Now we go to this pair, 5 and 3. We are good. 6 and 2. We are still good. Now note this is also highlighted here because if we actually move this unsorted element down here, then we should keep checking every other element to make sure it travel to the right place. But anyway, 6 is in the right place, so we are fine. And then we move on to the next one, 10, 5, and 3, and we are still good. Wow, so not much work to do here. And then again, 9, 6, 2, it's all in the right place. And finally, we get to the last element of the list. Now 8 is smaller than 10, so we do have to move 8. And then once we move 8 here, we have to check one gap away. Do we still have to keep moving it? But in this case, we are fine because all these this list or this part of the list is already 2 sorted, so it's fine, and we are done with gap of 2. And then finally, gap of 2, the next gap is well, we have nowhere to go but to gap of 1. So and this, when gap is equal to 1, this kind of becomes the insertion sort as we knew it. So and it's guaranteed to sort the entire thing. And the good thing is that because this list is already nearly sorted, most elements, they are already in the right place other than 3 and 2. So if you run through the insertion sort in this list, is really fast. It's almost O of n linear, and we are done. So now that you've seen how shell sort works in a small demo list, I would actually encourage you to go to our favorite visualization tool and kind of look at the animation for shell sort, but don't just look at it as a pretty animation, but know what it should do, and then run it through and make sure that what it actually does is matches what you expect it to do. So if you run through it, I mean, the first thing is, yeah, the gap is half of the size of the list, and then the gap becomes half of that, and then again the gap becomes half of that, and then finally, when the gap is small enough, you can kind of see, at the final step, the elements don't travel very far because the earlier step already kind of moved them closer to their destination, and that's what gives shell sort its speed.